Welcome to Elementary Functions. Today we're going to talk about parametric equations, implicit equations, and conics. My name is Wendy Fresh. I'm from Portland Community College, and this is Math 112. The objectives for this lesson are to graph parametric equations by hand, and specifically to describe horizontal and vertical movement, find a rectangular equation for a curve defined parametrically, and use it to describe circular and elliptical movement, and finally to express circles and ellipses as implicitly defined equations. All right, so we'll begin with graphing parametric equations by hand. And to do that, let's consider a figure skater carving a figure 8 on the ice. The following figure shows the skater's path embedded on a coordinate plane. Is this figure a function? Why or why not? Although the figure is not a function, because it fails the vertical line test, at each moment in time, the skater is in exactly one location. In other words, the skater's location is a function of time. We can use a system of parametric equations to define the skater's location as a function of time. A system of parametric equations consists of a pair of functions, one that describes the x-coordinate and the other that describes the y-coordinate. Typically, the input variable for these functions represents time. So let's let x equal f of t and y equal g of t, where f and g are two functions whose common domain is some interval I. The collection of points defined by x, y will be f of t and g of t. And that's called in a plane curve. The equations x equals f of t and y equals g of t, where t is in I, are called parametric equations of the curve, and the variable t is called the parameter. So let's take a look at an example. The following system of parametric equations describes the skater's motion that was graphed on the previous slide. X of t equals 4 times sine of pi over 2t, and y of t equals 8 times the cosine of pi over 4t. And we're on an interval from t equals 0 to 8, where t is measured in seconds. In other words, the first 8 seconds of skating. And x of t represents the horizontal movement of the skater, and y of t represents the vertical movement of the skater. So our job is to figure out how that figure 8 came about. And we can do that by filling in the values to the right to verify the graph from the previous slide. So you can see that my table of values looks a little bit different than what we've seen in previous courses. Normally, we have an input and we have an output. In this case, our input is t, and then we will have two outputs, one for x and one for y, and that's what we end up plotting as our point. So let's start with looking at t equals 0. If I were to put 0 into the x of t function, so in other words, what is x of 0? Now I'm not going to have room to do all of that work, so you're going to want to do some of this yourself, but let me just do a couple of the beginning ones. X of 0 would be equal to 4 times the sine of pi over 2 times 0. So that gives me 4 times the sine of 0, and the sine of 0 is 0, and 4 times 0, of course, is 0. So x of 0 is 0. And how about y of 0? Y of 0 is going to be 8 times the cosine of pi over 4 times 0. And the cosine of 0 is 1. So y of 0 is 8. So here's what that means. That means at 0 seconds that the skater is at a location of 0, 8. Go ahead and pause the video and see if you can fill out the rest of this table, and then come back once you've got it completed to see if your answers match mine. So now that you've had a couple of seconds to do that, let me just put in the values that I got. At 1 second, I had an x value of 4 and a y value of 4 root 2. I'm going to go ahead and estimate that 4 root 2, or not estimate, but use my calculator and approximate it at 5.66. At 2 seconds, I'm at 0, 0. At 3 seconds, I'm at -4 and -4 root 2. So that's -4, comma, -5.66. At 4 seconds, I'm at 0, -8. At 5 seconds, I'm at 4 and -4 root 2. So 4, -5.66. At 6 seconds, I'm back at 0, 0. At 7 seconds, I'm at -4. And for the y value, I'm at 4 root 2. And at 8 seconds, I'm at 0 and 8. So can our calculators graph something like this? The answer is yes. On a handheld calculator, you're going to go to Mode, and you'll change the graph type to Parametric to verify that the system of parametric equations given on the last slide actually do describe the skater's motion that was graphed as a figure 8. Before I show you the calculator, let's just verify that some of the values that we came up with on the previous slide we can see on this figure 8. So you've got your notes in front of you. The first point that we came up with at t equals 0 was the point 0, 8. So notice I have an x-axis and I have a y-axis. At 0 on the x-axis, I am up at 8. So this is where the skater is beginning. In other words, we could even label this t equals 0. Now, as 1 second goes by, the skater moves to the point 4, 5.66. So that is about right here in the first quadrant. So the motion of the skater is in a clockwise pattern. So this point would be after 1 second. After 2 seconds, it looks like I'm at the origin. At 3 seconds, I'm down in quadrant 3. Now the arrows are on there. If they weren't there, you'd want to make sure that you put them in. At 4 seconds, I am at 0, -8. At 5 seconds, I'm at 4, -5.66. I'm going to throw a couple arrows in there. At 6 seconds, I come back to 0. So t equals 2 and t equals 6. I was at the same value. At 7 seconds, I'm up in the second quadrant. And finally, I make my way back to where I began. So t equals 0 and t equals 8 are the same value. So here is a screenshot of a TI-84, and I know that a lot of you may have a TI-84. If you don't, there's also ways to do things like this using Desmos and GeoGebra. But I wanted to just point this out because I know so many of you do have the TI-84. What I said in the instructions was to go to Mode on your calculator. So let's just make sure you know where Mode is at. Mode is this red key that's in the upper left of your calculator, and when you press that button, you'll get a screen that looks like the screen that's in my image. And if you cursor down to the 1, 2, 3, 4, 5th line, you'll notice that you've probably never even seen this before, but we've always graphed our functions, but in this case we're going to change it to parametric. So you're going to arrow over, use your arrows, and change it to parametric. And then once you've done that, when you go to y equals, you'll notice that you have a screen that's different than what you've seen before. Now you've got an x sub 1 and you've got a y sub 1, and instead of having the input be x, notice that my variable is t, and that t matches the t that's being given to me in my parametric equation. Now you might be wondering how to get that t. Well, in the past you've oftentimes hit the button that's to the right of the green alpha key. Notice that that key is usually what we've used for x, but it also says t and it also says theta. So that is the button that we will pick, and when we're in parametric mode, the calculator will automatically know that we want a t and not an x value. Example 2. Suppose that the x and y coordinates of the movement of a robot are given by the function x of t equals 6 minus 2t and y of t equals negative 2 plus 4t. And this time t is still in seconds, but only for 0 to 3 seconds. So we've limited that input. But we still want to make a table of values and use it to sketch the graph of the robot's movement, using arrows to show the path and the direction of the robot. All right, so let's see here. I've gone ahead and put 0, 1, 2, 3. At some point, I'm going to let you choose what the t values are, but these seem like good values. And of course, there's a lot of other values between 0 and 3. I could put half units in there. I could put quarter units. If at any point your graph doesn't look complete, then all you need to do is graph more points by making the increments smaller. So let me do some work down here at the bottom. We'll start with t equals 0. What is x of 0? X of 0 is 6 minus 2 times 0, or 6 minus 0, which is 6. Y of 0 will be negative 2 plus 4 times 0, or negative 2. And that gives me the ordered pair 6, negative 2. How about x of 1? That's going to be 6 minus 2 times 1. 6 minus 2 is 4. And y of 1 is negative 2 plus 4 times 1. Negative 2 plus 4 is 2. Go ahead and pause the video and finish filling out the table. And now that you've come back, hopefully you got the same values as I did. And so now I'm going to go ahead and plot those values on my graph. So on my XY axis, I'm going to go to the right 6 and I'm going to go down 2. And that point is where I'm starting. So I'm going to label it as t equals 0. Then my robot moves to 4, 2. And that's going to be t equals 1. So I'm going to connect those. And I'm going to put an arrow to indicate that the movement of the robot is from right to left. And then the point 2, 6, that's happening after 3 seconds. Notice that when I do that arrow, it's not on the end, it's just somewhere in the middle to show the motion. And finally, at 3 seconds, I'm at 0, 10. So that's t equals 4. Now the reason I said that about the arrow is because what I don't want you to do is put an arrow on the 0, 10, because that would indicate that it's a line that keeps on going. This actually is going to stop at t equals 4 because of our limitation on time. So that is the graph of our parametric equation. So on the last slide we showed that we are able to graph parametric equations by hand. Now we want to find a rectangular equation for a curve defined parametrically. And from the graph on the previous slide with the robot, we can determine that the robot is moving in a linear pattern. I think you would agree with that. By eliminating the parameter t in the parametric equation above, the parametric equation can be rewritten as a rectangular equation that involves only the variables x and y. So what identifies a parametric equation is that variable of t. If I can get rid of the t, then what I will do is create a rectangular equation. So in other words, going back to my rectangular system. So it's a little bit like solving systems of equations. Let me start with the first equation for x. I'm going to say x is equal to 6 minus 2t. And because y also is in terms of t, what I'm going to do to try and eliminate the t variable is solve one of these equations for t and then substitute it into the other. I'm sure you've done something like this in a past math class, but maybe not quite like this. So I'll subtract 6 from both sides. I'll get x minus 6 equals negative 2t. I'll divide by negative 2, and so I end up with t equaling x minus 6 over negative 2. Now, I'm going to take that and I'm going to substitute that t value in with x minus 6 over negative 2. And I'm going to simplify. Now, because I'm multiplying, I can cross-reduce the 4 and the negative 2 and then distribute that through. So that cross-reduces to negative 2. And negative 2 times x is negative 2x, and negative 2 times a minus 6 is plus 12. So I end up with y equals negative 2x plus 10. So the rectangular equation is y equals negative 2x plus 10. And you might recall that we had a limitation on t. We said that the t values were between 0 and 3. If we've eliminated the t variable, then we have to rewrite that restriction on the domain in terms of what our new domain is, which is x. So in other words, when you go back and look at the picture of that robot's movement, along the x-axis, we only saw x values from what to what. And if you go back and look at that, I think that you'll see that those x values are from 0 to 6. Now, you can either look at the graph, or because we're going to look at restrictions of x, if x can only be equal to 6 minus 2t, and t can only be between 0 and 3, then the outputs or the limitations for x are simply found by substituting in 0 and substituting in 3. And that gets me 6, and that gets me 0. And so I see my limitations. All right, so let's take a look at another example. The x and y coordinates of the movement of a particle are given by the following function of time t, where 0 is less than or equal to t is less than or equal to 2 pi. So we have a trig parametric equation now. X of t is equal to 3 plus the cosine of t, and y of t is equal to 2 plus the sine of t. And again, we're going to make a table of values and use it to sketch the graph. Now, in this case, I did not put any values in for t, so it will be up to us to decide what we want to use. Of course, the limitations that I have are 0 to 2 pi. So I'm going to use the space that I have and probably start with 0 and go all the way to 2 pi. Maybe halfway in between, I will be at pi, and then halfway between there, pi over 2, and then maybe 3 pi over 2. I'm going to see if that's enough. If that's enough to get a good idea of what the picture is, I don't need to graph any other points. But if it's not, I've got the room. All right, so let's see here. We've done this a few times. I'll do it for just the first couple. Let me go ahead and work with pi. And so I'm going to say x of pi is equal to 3 plus the cosine of pi. And let's see, the cosine of pi is -1, and so that puts me at -2. And for my y value, y of pi, and it feels weird to say y of pi, but pi is just a number, 3.14, so there's nothing wrong about writing it. We're just not used to it. The sign of pi is 0, and so 2 plus 0 is 2. And so that gives me the ordered pair -2, 2. So go ahead, pause the video, fill in the rest of these points, and then we'll plot them together. All right, so for time equals 0, I got the ordered pair 4, 2. For pi over 2, I got the ordered pair 3, 3. For 3 pi over 2, I got the ordered pair 3, 1. And for 2 pi, I got 4 and 2. So it looks like I wind my way back. So let's plot these points. So movement from the origin 4 and then up 2. So that's where I'm going to be at t equals 0. At a time of pi over 2, I'm at 3 and 3. So that's t equals pi over 2. So I'm going to connect those in a little bit. I'm going to put an arrow here just to remind me the direction. The reason I'm not connecting them right now because I don't exactly know how I should connect them. Do I connect them with a diagonal or do I connect them with a curve? Now I have a guess based off of the parametric equation. You be thinking about that as well, and we'll see if we're right. When time is pi, I'm at -2, 2. So that's at t equals pi. And at 3 pi over 2, I'm at 3, 1. And finally, I round my way back. Now, one of the ways, I guess, that I could draw this is by drawing hard lines, just connecting like that. I could find out if I'm right by maybe plotting just a few other points. If I were to put in, let's say, pi over something in between 0 and pi over 2. So let's just say I put in pi over 4. Then I would have, let me actually start with x. I would have x of pi over 4 equals 3 plus the cosine of pi over 4. So 3 plus root 2 over 2, which is approximately, let's see, I get around 3.7. And y of pi over 4 is going to be 2 plus the sine of pi over 4. So 2 plus root 2 over 2, which is approximately 2.7. So let me put those numbers in. All right, so is that enough evidence to tell you whether or not we connected them correctly? It tells me that we did not connect them correctly, because if it was supposed to be a line, then this point that would be halfway in between 3 and 4 should probably be giving me a 3.5 value. And the fact that I'm at 3.7 tells me that I'm actually maybe just a little bit outside of that line. And then the other thing that I'll say is the fact that I'm dealing with sines and cosines tells me that there's probably a circular motion to this. So my guess would be that instead of looking like a diamond, maybe this thing actually looks more like a circle. So now we're going to find a rectangular equation for a curve defined parametrically. From the graph on the previous slide, we think that we can determine that the robot is moving in a circular pattern. That is our guess at this point. By eliminating the parameter t in the parametric equation above, the parametric equation can be rewritten as a rectangular equation involving only the variables x and y. So let's see what we've got here. We've got x equals 3 plus the cosine of t, and we've got y equals 2 plus the sine of t. What makes this a little bit more challenging than the one that we did before with the lines is with the lines I could actually solve for t. If I try to solve one of these for t, then I bring in an inverse, and it feels as though that might make it more difficult. I think it could be done, but it might be more difficult. What I'm going to do instead is make use of one of our identities. And the identity that I'm thinking of is the Pythagorean identity. And I'm thinking of that one because that one involves both sine and cosine, which I have. So what I'm going to do with the x equation, I'm going to subtract 3 from both sides. And I'm left with x minus 3 equals the cosine of t. Now, if you remember, I just said I want to use the Pythagorean identity. Now, in order to make that happen, I need cosine squared of t. So I'm going to square both sides. I'm going to do the same thing with the y. So I get y minus 2 equals the sine of t. I'm going to square both sides. And so I get y minus 2 to the second power equals sine squared of t. Now, this may feel strange, but I would imagine that at some point in your algebra life, you learned a method called the elimination method, which basically says if you have two things that equal each other, so let's say A equals A and B equals B, then if I add those two things, I still have something that's equal. So that's what I'm going to do here. It's just that our things that are equal don't necessarily look equal. Let me show you what I mean. I have x minus 3 squared, and that's equal to cosine squared t. I have y minus 2 squared, and that's equal to sine squared t. Because they both equal each other, I'm going to add them, and that gets me x minus 3 to the second power plus y minus 2 to the second power, and that's going to equal cosine squared t plus sine squared t. Now, we have the Pythagorean identity, and so we're going to say x minus 3 to the second power plus y minus 2 to the second power, and that equals 1. So the rectangular equation, which simply means that the only thing in this equation are x's and y's, is x minus 3 squared plus y minus 2 squared equals 1. That certainly doesn't look like anything involving lines. In fact, with the square, I think of more a curve motion. So although the single rectangular equation might be more efficient than the system of parametric equations, the advantage of the system of parametric equations is that the parametric equations give us a direction. In other words, when we graph a line, we don't know if the movement is from left to right or right to left. With a parametric equation, we get to see and learn something about the movement of the particle, or I guess I could say the path that it is taking. All right, so now we're ready to express circles and ellipses as implicitly defined equations. The parametric equation from the previous slide was found to be circular. The rectangular equation can be written as x minus 3 squared plus y minus 2 squared equals 1. And it's called implicit because neither of the variables is isolated on one side of the equation. In other words, we don't have x equals or y equals. We could not put this into our graphing calculator if we were in function mode. However, if we solve the implicit equation for y, then the result will be what we call explicit. Explicit because one of the variables is isolated on one side of the equation. So it's not the nicest or the prettiest thing to look at, but it's possible. So let me show you. If I have x minus 3 squared plus y minus 2 squared equals 1, and I want to isolate a variable, if I have thoughts about putting this into my graphing calculator, I might subtract x minus 3 squared from both sides. Now I'm not going to worry about multiplying that out. I'm just worrying about getting the y by itself. And I actually think that if I were to multiply it out, it would make it worse, because then I would have a y squared and a y. So I need to get that y untrapped from the square. So if I square root both sides, then I get y minus 2 equals plus or minus the square root of 1 minus x minus 3 squared. Now, can I take the square root of x minus 3 squared and call it x minus 3? I cannot. And the reason I can't is because that x minus 3 squared is part of it's a term because it's connected by addition and subtraction. So the only last thing that I can do is get the y by itself by adding 2 to both sides, and I get 2 plus or minus the square root of 1 minus x minus 3 squared. And that's a little bit hard to read, so I've left us some space on this line. Y equals 2 plus or minus the square root of 1 minus x minus 3 to the second power. So why do you think this is so much more complicated? Well, if the original equation x minus 3 squared plus y minus 2 squared equals 1 actually is a circle, is that something that we could input to our calculator in function mode? And the answer is no, because a circle is not a function. A circle would not pass the vertical line test. So if we want to write it as an explicit equation, in other words, write it in y equals form so that we can put it into a calculator, then we have to take that circle and we have to break it up into 2 pieces, each piece being a function, but when put together make a circle. And that's what the plus and minus is there for. One of those pieces gets me the top part of the circle, the other piece gets me the bottom part of the circle. So certainly you can see that in some cases parametric may be the way to go, or in other cases implicit equations may be the way to go, and in other situations maybe explicit is the way to go. All right, so in general, for a circle, for r greater than 0, the parametric equation of a circle of radius r centered at the point h comma k is x equals h plus r times the cosine of t, and y equals k plus r times the sine of t, where t is from 0 to 2 pi. And then if we take that parametric equation and we rewrite it as an implicit equation, we will always get a radius of r centered at the point h comma k, and the form will be quantity x minus h squared plus quantity y minus k squared equals r. Now, let me just point out a couple of things here. The center in the parametric is hk, so those are the numbers that are on the outside. And when we have r's in front of the cosine and the sine, that r is going to be our radius. We see that same h and we see that same k in the implicit equation, and then we see r squared on the end. So I went ahead and put this into Desmos. I showed you how to do this on the graphing calculator. I'm not sure how well you can see this, but what I did is in Desmos, I entered it as a point. In other words, normally in Desmos, we can enter an x and we can enter a y. Well, in the original parametric equation for this, we were given, let's see if I can remember what that was. It was x equals 3 plus the cosine of t and it was y equals 2 plus the sine of t, and I guess it's actually written right in front of me, right here. It's just not written as x equals and y equals, but that's why we write it like this in Desmos, because instead of saying x equals y equals, we just write it as an ordered pair. And Desmos automatically knows when it sees that input of t that it's a parametric equation. Now the only thing Desmos doesn't do is tell us where do we start and where did we end, and we had to do that by hand. The other thing that I want to just point out is that when we took that parametric equation and we rewrote it as an implicit rectangular form, we got x minus 3 squared plus y minus 2 squared, and we said that that was equal to 1. So what I want to do now is just make sure that the general formula that I just gave you works here and that we can see it. Let's first talk about the center. The center, it says, is at HK, and H and K are these numbers that are outside of the parametric. So 3, 2, and then 3 and 2 on the inside. Notice that on the inside of the implicit, we see the power of transformations. Whenever you have a minus on the inside, transformations tell us that it does the opposite. So if I go to 3 and then up to 2, sure enough, there is my center. And then the radius is the number that is on the outside of the sine and the cosine. Now that number has to be the same. In this case, we don't see anything there, which means that there's a 1. And then the other place that we see r is on the end of the implicit equation. So this number right here is equal to r squared. And it just so happens to turn out that if I square root, I also get 1. So if I go from my center to the right, if I go up, if I go to the left, and I go down, sure enough, I have a radius of 1. Now you might recall, if I wanted to write this down, this should be the same picture that we got when we did it by hand. We just weren't sure what to do at t equals 0. Let's say t equals 0 to t equals pi over 2. We weren't sure how to connect those 2 points. Now we can see, we had a pretty good guess, but now we can see for sure that it is with a curve. What graphing it by hand does, again, for you is it allows you to put direction, and it also allows you to see when in each moment of time, in this case, if this were a robot, it shows you in each moment of time the path of that robot. So let's try another example. The x and y coordinates of the movement of a particle are given by the following function of time t, where 0 is less than or equal to t is less than or equal to 2 pi. X of t is equal to 3 plus 5 times the cosine of t, and y of t is equal to 2 plus 3 times the sine of t. This time I'd like you to use a graphing device to try graphing. Either use your calculator or use Desmos to come up with a graph. And here is the picture that I got, and you'll see my warning. If you're not careful about using zoom square, what looks like an egg on mine, a horizontal egg, could end up being a vertical egg. Now what I mean by that is if you think about what the normal window is of a computer screen or a laptop or your graphing calculator, usually the vertical axis is wider than, or excuse me, usually the horizontal axis is wider than the vertical. And so that tends to distort things. By changing it to zoom square, you make sure that each one of those little boxes is a square and that it's correctly graphed. So from the graph on the previous slide, we can say that the particle is moving in what we say an elliptical pattern. And we'll go through the process that we saw earlier with the circle, where we will eliminate the parameter t in the parametric equation, and therefore rewrite the parametric equation as a rectangular equation where we're involving only the variables x and y. So I'm going to use the same technique that I used before. I have x equals 3 plus 5 times the cosine of t, and I have y equals 2 plus 3 times the sine of t. And if you recall from last time, what I did was I isolated the sine and the cosine so that I could then square it and use the Pythagorean identity. I'm going to try that again. So that's going to get me x minus 3 equals 5 times the cosine of t. And I think I'll take that one step further. I will divide by 5 so that I can get that cosine by itself. And then y minus 2 equals 3 times the sine of t, and y minus 2 over 3 equals the sine of t. Now, if I square both sides and add, I can make use of my Pythagorean identity. So adding straight down, I get x minus 3 squared over 25 plus y minus 2 squared over 9, and sine squared t plus cosine squared t is 1. All right, so now in general for an ellipse, here's what we've got. The parametric equation of an ellipse centered at a point h, k, hk, is given by x equals h plus a times the cosine of t, y equals k plus b times the sine of t, where t is between 0 and 2 pi. So there's my h and my k on the end again. We don't have a radius this time. And what you may or may not have noticed is that there were different numbers in front of the sine and the cosine. That's what gave it that elliptical shape. In other words, you might think of it as the horizontal radius was different than the vertical radius. An implicit equation for an ellipse centered at the point hk, and with the length of the horizontal axis as 2a and the vertical axis as 2b, is given by x minus h squared over a squared plus y minus k squared over b squared equal to 1. The longer axis is called the major axis, and the smaller axis is called the minor. All right, so let's dissect what we've got here. We started out with the parametric equation, x equals 3 plus 5 times the cosine of t, and y equals 2 plus 3 times the sine of t. And then we rewrote it as an implicit equation, and we got x minus 3 squared over 25 plus y minus 2 squared over 9 equals 1. All right, so let's see here. HK, that's going to be our center. So let's start with that. H and K are these numbers on the front end of the parametric. So my center should be at 3, 2. So if I start at the origin and I go to the right 3 and then I go up 2, sure enough, there is my center. If I go from the center to the right, I go 1, 2, 3, 4, 5 units, and to the left also 5 units. And that's because the number underneath the x is 25, and 25 is coming from 5 squared. So let's remember what it said here. The horizontal axis, which is what we're dealing with, is equal to 2 times a. Well, my a value is the number that I squared, and in my case that was 5. So my horizontal axis should have a length of 2 times 5, or 10. Now what we mean by that is not the radius, but more like a diameter. So our horizontal axis has a length of 10. And because it's the longer axis, we would also say that this is the major axis. Now, for the vertical, from the center we go up 1, 2, and 3, and we go down 1, 2, and 3. And that's because the number in the denominator is 9, which comes from 3 squared. The vertical axis has a length of 2b, and my b value is the number that I square. In my case, that's 3. And 2 times 3 is equal to 6. And sure enough, my minor axis, or my vertical axis, has a length of 6. So now we're just going to work a lot of examples so that you get a taste of all the sorts of problems you might see. The first one says to sketch a graph of the following parametric equation where t is between 0 and 2 pi, x of t is equal to 3 plus 4 times the cosine of t, and y of t is 2 plus 4 times the sine of t. Now you should also make sure that you can input this into a graphing device and get a picture that you're happy with. Make sure that if it's a picture you're not happy with, that you pay attention to what your settings are. In other words, what values do you have, or what are your window settings for your t values? So here's my space. Now, I don't have to graph this by hand. Like I said, you want to use a graphing calculator, but I also think that based off of what we said about the summary, that there's some things that we can notice here, and things that we can notice to the point that I don't think we have to make a table of values. For example, I know that these numbers that are out in front, in other words, the 3 and the 2, represent my center. All right, so I'm going to go to the right 3 and I'm going to go up 2. And then the other thing I notice is that the numbers in front of the sine and the cosine are the same. And when they're the same, that means that they have the equal distance from the center to the edge of the shape. So in this case, that makes it a circle. And it's going to be a circle of radius of 4. So from that center, I'm going to go to the right, 1, 2, 3, and 4, and up 1, 2, 3, and 4, and left 1, 2, 3, and 4, and down 1, 2, 3, and 4. And I'm going to connect those with a nice smooth curve if I can, something that looks circular. Certainly my graphing device will do a better job. And then the only thing else that I need to do is determine where does this circle start and in what direction does it go. So what I would recommend, you don't have to input too many values, but let me start with t equals 0. If t equaled 0, what would x of 0 be and what would y of 0 be? Well, x of 0 would be 3 plus 4 times the cosine of 0, which would give me 7. And y of 0 would be 2 plus 4 times the sine of 0, or 2. So let me find 7, 2. 7, 2 is right here. So that's my start point. That's at t equals 0. And then let me do one other point. How about, let's just do pi over 2. That'll get me my direction. And that's a pretty easy one to quickly get some values for because I don't anticipate any decimals. So 3 plus 4 times the cosine of pi over 2. Cosine of pi over 2 is 0, so I end up with 3 plus 0, or 3. And then 2 plus 4 times the sine of pi over 2, which is 6. So where am I at with 3 and 6? It looks like I am straight up at the top. As long as you find the direction, you can then just do the arrows all the way around. And if you want, and it's indicated, go ahead and put the rest of the times on the graph. Usually though, the arrows and the starting and maybe one other value is enough to show that you are clear on the direction that the circle is going. Now, what would an implicit equation for this parametric curve be? So you've got your notes in front of you, and so if you use those notes, you know that the parametric is going to be, or excuse me, the implicit is going to be x minus the first value of the center squared plus y minus the second value of the center squared, and that's going to equal r squared. So in my case, 4 squared, or maybe you want to write that as 16. Example 6. Sketch a graph of the following parametric equation from 0 to 2 pi. X of t equals 7 plus 2 times the cosine of t. Y equals 4 plus 5 times the sine of t. And if you'd like, use a graphing device or challenge yourself to see, could I plot this without a graphing device? So here's what I know. I know that this has a center at 7, 4. And I can see that this is not going to be a circle because the numbers in front of the sine and the cosine are not the same. So let me plot that point 7, 4. So to the right 7 and then up 1, 2, 3, and 4. There we go. And the 2 in front of the cosine tells me that I'm going to go to the right 2 and to the left 2 to get my horizontal distance. And then I'm going to go up 5, 1, 2, 3, 4, 5 to get my vertical, and down 1, 2, 3, 4, 5 to get my other vertical. And I can see that oval or elliptical shape forming. It's going to look something like that. Sometimes they ask other questions like, what is the major axis, or what is the minor axis? In this case, I would say for sure that the major axis is the y-axis because it's longer, and the minor axis is the x-axis. And they might even want to know what's the length. So what is the length? Well, if we've plotted it, we can just count. We went, let's see here. For the y-axis, we went up 5, we went down 5, and so that would be a length of 10, or from our formula, that's going to be 2 times 5. And for our minor axis, if we just count, we've got 2 and 2, which is 4, or that's 2 times 2. Where did we start? Well, I'll let you do the computations for this. I'm going to tell you, though, that I've done the computations already, and I show that I started at the point 9, 4, and then I input pi over 2 and found it to be at 7, 9. And so that told me that I was going counterclockwise. Don't think that it's always counterclockwise, though. In some cases, it might fool you. The implicit equation for our ellipse is going to be x minus 7 to the second power over that 2 to the second power plus y minus 4 to the second power over 5 to the second power, and it always equals 1. If you would like to square the 2 squared and call it 4, and square the 5 square and call it 25, you can. You could also FOIL the numerators, but to be honest with you, leaving it in factored form tells me a lot more information than foiling it would. So I would probably leave it just the way it is. All right, let's look at example 7. It says, what are the center and the radius of the circle? 2x squared plus 8x plus 2y squared minus 12y equals 24. And in this particular case, they give us that it's a circle, which is a good thing because this does not look like a circle at all. But it is a circle, and so what we know is that we need to rewrite it in a form that we can get it into. This is going to be, well, first of all, this is an implicit equation because it's not solved for x or y, and there is no parameter of t, so I know it's not a parametric equation. So the implicit form for a circle that we can recognize is x minus h squared plus y minus k squared, and that's going to equal r squared. So what I need to do is I need to rewrite this equation with perfect square binomials. That's what the x minus h squared and the y minus k squared are. But before I do that, I'm going to simplify this equation by dividing all sides by 2. And when I do that, I think I make it look a lot better. I get x squared plus 4x plus y squared minus 6y equals 12. Now the process to create that perfect square binomial is called completing the square. Have you heard of that before? It's usually taught in a beginning algebra course, but it's been a while for you, so let me refresh your memory. I'm going to take the x squared plus 4x, and I'm going to create a space, and I'm going to scoot that y squared minus 6y down and create a space and put the 12 on the end. Now what that space is for is I want to create a number to go in both of those spaces that's going to allow me to factor these into perfect square binomials. Now the process to do that is you take this, what they call b value, which for the first part is 4. I'm going to take half of 4, which is 2, and then I'm going to square that 2 to get 4. That 4 is what I'm going to add to get my perfect square binomial. Now if I add 4 on the left, I have to add 4 on the right. Now let me show you what happens here. X squared plus 4x plus 4 factors to x plus 2 to the second power. And what's really nice is that this 2 comes from the number that I took half of. That'll always be the case. For the y, I'm going to do the same process. I'm going to take half of negative 6, which is negative 3, and negative 3 squared is 9. So I'm going to add 9 on the left, and I'm going to add 9 on the right. When I factor y squared minus 6y plus 9, I get y minus 3 squared. Remember where that minus 3 comes from? It's the number before we squared it. And then the only thing left for me to do is to figure out what is 12 plus 4 plus 9. And I think that that is 25. So now I've written it as the implicit form of a circle, and so I can answer the original question. The center is going to be negative 2, positive 3. Remember, when it's written in this form, it's like a transformation, so it does the opposite of what you might think. And the radius is going to be the square root of 25, or 5. Example 8. What are the center and the lengths of the horizontal and vertical axis of the ellipse? All right, so we have 4x squared plus 16x plus y squared plus 2y plus 13 equals 0. And so it's not a parametric because we do not have the parameter of t. What I know about an implicit form of an ellipse is that I have to get it in the form x minus h squared over a squared plus quantity y minus k squared over b squared, and it's always going to equal 1. So because I'm talking about perfect square binomials again, I'm going to expect that I'm going to have to complete the square. Before I do that, is there anything I can divide through on both sides? And I think the answer is no. I can divide part of it by 4 or by 2, but not all of it. All right, so let me just rewrite what I've got. I'm going to create a little space there. and I'm going to move the 13 over to the other side. One of the things about completing the square is that you can only complete the square if you have a coefficient of 1 in front of your x squared and your y squared. I have that for the y squared, but I don't have that for the x squared. So I'm going to take care of that problem by factoring out a 4. I'm going to factor that 4 just out of the 4x squared plus 16x. In other words, I haven't changed the problem, I've just made it look different. All right, so I'm going to take half of 4, which is 2, and then I'm going to take 2 squared, and that gives me 4. So I'm going to put a plus 4 on the inside. Now here's where it's a little bit tricky. What did I add to the left-hand side? And your answer might be 4, but because that 4 is inside of the parentheses, it gets affected by the 4 that's on the outside of the parentheses. So what I really added to the left was 4 times 4, or 16. So I have to add 16 on the right. You only have to worry about that when you have to factor something out to get 1 as your coefficient. I'm not going to have to worry about that for the second part because I already have a 1. Half of 2 is 1. Half of 2 is 1, and 1 squared is 1. So I'm going to, let me just go ahead and put, I'm going to put plus, I guess I'll just do it here, y squared plus 2y plus 1. And so I'm going to plus 1 here as well. And so let me just create a little spot. I'm going to get 4 times x squared plus 4x plus 4 factors to x plus 2 squared. Remember where that 2 comes from. And then I'm also going to have plus y plus 1 squared. And of course we know where that 1 came from. And that's going to equal, what is negative 13 plus 16 plus 1? I think that is equal to 4. Now, I'm not quite there because one thing I know for sure about the implicit form of an ellipse is that it has to equal 1. So I'm going to get mine to equal 1 by dividing through by 4. If I divide the right by 4, I have to divide the left by 4. Now a nice thing happens with my first term. The 4's cancel out, so I'm left with x plus 2 squared. Now we're expecting an a squared on the bottom, so that doesn't throw you. Let's just put a 1 under there, plus y plus 1 squared over 4, and that equals 1. So now I have it in the form I need, and I can say that this has a center of -2, -1. It's always the opposite of what you see on the inside of the parentheses. My a value, let's see here, my a squared value is 1, so my a value is the square root of that. My b squared is 4, and so my v value is the square root of that. And let's see, what else did they ask me? So I have the center, and now how about the lengths? Well, the horizontal length is going to be 2 times that a value, or 2, and my vertical length is going to be 2 times my b value, or 4. And I didn't ask you to do it on this one, but I would hope that with this information you would be able to graph it and then identify the major and minor axis. Example 9. The position of a projectile fired with an initial velocity v sub 0 feet per second, s sub 0 feet above the ground at an elevation angle of theta after t seconds is given by the parametric equations x of t equals v sub 0 times cosine of theta t, and y of t equals negative 16t squared plus v sub 0 sine of theta t plus s sub 0. A batter hits a ball that is 3 feet above the ground and leaves the bat with an initial velocity of 138 feet per second, making an angle of 26 degrees with the horizontal. The ball is heading toward a 25-foot high fence that is 400 feet away. Part A says to write an equation that gives the horizontal distance of the ball at any time t. So the horizontal distance is my x of t. And I've got an equation for that. X of t is equal to v sub 0, and v sub 0 is my initial velocity. And they tell me that my initial velocity is 138 feet per second. So I'm going to put 138 there. And then the cosine of my theta, which is 26 degrees, and t. So that's my equation. For part B, it says to write an equation that gives the vertical height of the ball at any time. So the vertical is the y of t. So I have negative 16 t to the second power plus my v sub 0, which I already said was 138, times the sine of 26 degrees t plus s sub 0. S sub 0 is the feet above the ground. And let's see, I am 3 feet above the ground, so plus 3. And the question is, will the ball go over the fence? Well, the fence, let's see, the fence is 400 feet away, and that is a horizontal distance. So I'm going to set my x of t equal to 400. And let's see how long, in other words, solve for t. And so when I put all of that into my calculator, of course, what I'm putting into my calculator is t equals 400 divided by 138 times the cosine of 26 degrees. And when I put that into my calculator, I get 3.22 seconds. So that's, the fence is 400 feet away. It's going to take me 3.22 seconds to get 400 feet away. And the question is that after 3.22 seconds, how high will the ball be? So after t equals 3.22, what is the height? And remember that the height is my y value. So y of 3.22, if I put all of that into my calculator, into the negative 16t squared plus 138 times the sine of 26 degrees, all of that, plus 3, putting the 3.22 in, I end up with approximately 31.69, and that is in feet. So will the ball clear that fence? And that fence is 25 feet high. So yes, I will clear the fence.